As the title of this video suggests, in this video we'll be working a hard trig limit problem. And the problem we'll be taking a look at in this video is the limit as x tends to negative infinity of the arc cotangent, and in the numerator we have x to the 5th plus 3, denominator we have x to the 6th plus 8, and then we have a plus square root of 3 added to that, and we will be taking the arc cotangent of all of that and finding the limit as x tends to negative infinity. So where do we start? Well, we can first look at this expression here, and as x goes to negative infinity, this numerator will go to something really big raised to the 5th, and something really big and negative raised to the 5th, which will give you something even bigger and still negative because it's raised to an odd power, and then we'll be adding 3. So I'll just say large here x to the 5th plus 3 approaches negative infinity to the 5th is still negative infinity. This is just a large number, okay? So, and this is in the limit of it approaches. In the limit, this x, we're considering the limit as x tends to negative infinity. That's why it looks like I'm plugging in negative infinity. You can't really plug in infinity or negative infinity because they're not numbers, but for the idea, to get the idea across, instead of writing a very large negative number, I'm just writing negative infinity. You take that, raise it to the 5th, you get another very large negative number, even larger than the number that you're raising to the 5th, and you add 3 to it. It doesn't really make it all that much smaller of a negative number, so we'll just write this numerator as negative infinity. But x to the 6th plus 8 goes to, well, negative infinity raised to the 6th. A really big negative number raised to the 6th is going to be a really big positive number because this is an even exponent. You add 3 to a really big positive number, you will get a even bigger but positive number. So as x, well, we already have the as x tends to negative infinity, so that applies to both of these here. What happens to this ratio, x to the 5th cube, x to the 5th plus 3 over x to the 6th plus 8? Well, that's what we're going to look at right now. Alright, so I have negative infinity over positive infinity. Well, that's the same thing as negative 1 times positive infinity over positive infinity. And if you'll remember from the indeterminate forms video, this is an indeterminate form. Indeterminate form. So this means we have more algebra to do. So what do? Well, let's see how much space I have to work with. So I'm going to rewrite the problem here. It's the limit as x tends to negative infinity of the arc cotangent, and capital means principal arc cotangent, and we'll get to that in a second. It's basically turning this arc cotangent into a function. I'll explain that to you in a moment, though. Okay, so we said as well, we we said as x tends to negative infinity, this tends to -1 times positive infinity over positive infinity, which is an indeterminate form. If you remember from previous examples of finding limits of rational functions that initially appear to be indeterminate forms, we divided both numerator and denominator by the highest power of x present. And dividing both numerator and denominator by the same thing is equivalent to dividing by 1 or multiplying by 1, depending on how you look at it. So that's exactly what we're going to be doing here. We're going to be still working inside of this arc cotangent, but we are going to be multiplying this by 1. But a special version of 1 will be x to the 6th over x to the 6th. So we will divide both numerator and denominator by x to the 6th. And I'm only doing that to this. So I'm multiplying this expression here by a carefully chosen version of 1. So this is the limit as x tends to negative infinity. The principal, oops, I just wrote arc, should be arc cotangent. Arc cotangent of, we do this division here, we get 1 over x. Divide 3 by x to the 6th, we get 3 over x to the 6th. Should be a 6. Denominator, x to the 6th over x to the 6th is 1. We have a plus 8 over x to the power of 6. And then plus 3, plus the square root of 3, I should say. Okay, now we will look at this limit here. So as x goes to negative infinity, this 1 over x goes to 0. Arc cotangent, so this 1 over x goes to 0. This 3 over x to the 6th also goes to 0 because x to the 6th goes to a really big positive number as x gets to be a really big negative number. Raising x to an even exponent gives you a really big positive number. Then taking 3 and dividing it by that really big positive number is equivalent to breaking up 3 into a ton of chunks, and the size of those chunks will be very, very small. And so we will, this limit is all, or 3, as x tends to negative infinity, 3 over x to the 6th also goes to 0. 1 will just go to 1, of course, and 8 over x to the 6th, well, as x goes to negative infinity, x to the 6th is going to go to positive infinity. It will become a really big positive number. 8 over that really big positive number will be 0. Then we just have this plus the square root of 3 written here. So 0 over 1 is 0. So this is equivalent to the principal arc cotangent of 0 plus the square root of 3, which is just the principal arc cotangent of the square root of 3. Now what is this? What is this number? Well, this is asking what angle do I take the cotangent of to get the square root of 3? And this is a principal arc cotangent, and I'm going to go over what that means here in a second. So all of our work here led us to the limit as x tends to negative infinity of the arc cotangent, principal arc cotangent of x to the fifth plus 3 over x to the sixth plus 8 plus the square root of 3 is equivalent to the arc cotangent, principal arc cotangent of the square root of 3. So you may or may not remember from pre-calculus that this is how the arc cotangent function looks. So I'm just going to draw. It here and then explain it. So this is pi over 2. This is pi. So every integer multiple of pi, which includes 0 itself, you have a vertical asymptote. So the arc, this is just cotangent, okay? This is not arc cotangent. So this is f of x equals cotangent of x, okay? But this is just this isn't the entire graph, all right? This is this thing repeats. So if we have, say we have 3 pi over 2 here. You extend this out like so. 2 pi here. Imagine these were evenly spaced. So imagine each of these lines is pi over 2 apart. You'll have something like this. And to reason through why you have vertical asymptotes here, you just have to remember that cotangent of x is defined, and this 3 lines means defined, 2 lines is equal, but when you have 3 parallel lines like this, usually what that means is what's on the left side of those 3 parallel lines is defined to be whatever's on the right side. So it's defined to be cosine of x over sine of x. So hopefully you'll remember from the unit circle, and I did cover this in a previous video, but to jog your memory, I'll cover it again here. Oh dear, that is supposed to be a circle of radius 1, but it doesn't quite look like that. But bear with me. Let's assume this is a circle. This is the x-axis. This is the y-axis. This is x equals positive 1, y equals positive 1, x equals negative 1, y equals negative 1. And theta is measured with respect to the positive x-axis. This is theta here. Remember, every point on this circle can be represented as cosine of theta, comma sine of theta. And that's to say that cosine of theta is the x coordinate of on the unit circle, where theta is the angle swept in the counterclockwise direction from the positive x-axis. So if you were interested in cosine of, say, pi over 4, right? Pi over 4 is 45 degrees, or cosine of negative pi over 4. You'll go 45 degrees in the clockwise direction, so in the opposite direction that you would go to get to positive pi over 4. So if you wanted to find the cosine of negative pi over 4, what you do is you'd sweep theta pi over 4 radians, or 45 degrees, in the clockwise direction. That's the opposite direction for which you'd go if you're looking for positive pi over 4. So I'll call this theta 1. This is theta 2 equals negative pi over 4. And the x coordinate here on this unit circle, so that's at the terminal point of this ray here. And remember, a ray from elementary school geometry is a figure with it's basically a straight line, but it's one with a definite beginning point but no end point. Okay, but well, I should say the segment. This does have an end point. This is a so it's not a ray. This is a segment. So whose terminal, the segment whose terminal end is on the unit circle. So when the x coordinate of that segment, whose initial end's on the origin and the terminal end is where this little segment that we've drawn after we've swept theta, where it cuts where we've swept theta 2, or negative pi over 4 radians, 45 degrees from the positive x-axis, where it cuts the unit circle. That's going to be, the x coordinate of that is going to be cosine of negative pi over 4, and the y coordinate is going to be sine of negative pi over 4. And you can tell here that the x coordinate is positive, so cosine will be positive here. So this is positive, and sine will be negative here. So what does this have to do with the cotangent function? Well, cotangent of x is defined to be cosine of x over sine of x. So here we're looking at x equals 0. Between x equals 0 and pi over 2, when you're looking very close to 0, right? What's cosine? Cosine's very close to 1. But sine is very close to 0. So you're dividing a positive number very close to 1 by a positive number very close to 0. And you will get positive infinity. When you go towards pi over 2, at pi over 2, cosine is 0, because remember, cosine is the x coordinate, but sine is 1, and cotangent is cosine x over sine x. So cosine is 0, so 0, and sine is 1, so 0 over 1 is 0. At pi over 4, 45 degrees though, it looks like cosine, the x and y coordinates are about equal, and they are. Cosine of here, let's say theta 1 is, let's say it's pi over 4. So the coordinate here is going to be cosine of pi over 4 comma sine of pi over 4. And this is the square root of 2 over 2. Both of these are, and so this is equivalent to square root of 2 over 2 comma the square root of 2 over 2. So these are the same. So when you divide cosine of pi over 4 by sine of pi over 4, you're getting square root of 2 over 2 divided by itself, and that's 1. So at pi over 4, this is roughly, cotangent of x is roughly 1. But now going, and we said at pi over 2 it's 0, but now going towards pi, you'll notice right at pi, cosine of 0 is -1, and it's negative all through here between pi over 2 and pi. But sine of 0, which is the sine of pi, is 0. So you'll be having very close to theta equals pi. You will be having a cosine of something very close to -1, but a bit smaller, and sine of something that's positive but a very tiny fraction. So like -0.99999 divided by positive 0.0001 will be a very big negative number. So as theta or x gets closer and closer to pi, but coming from pi over 2, you'll notice that this ratio of cosine of x over sine of x, which is cotangent of x, gets closer. It gets bigger and bigger and bigger, but in the negative direction. And here you'll see this just repeats. So we'll look at this. We're in the third quadrant, so both the x and y coordinates are negative here. And remember, sine is the y coordinate and cosine is the x coordinate. And when you're looking very close to -1, the cosine is going to be negative but very close to -1. The sine is going to be negative but very close to 0. So you'll have a number very close to -1 cosine divided by, but a little bit less than it, so like -0.99999, less on in terms of magnitude. A little bit smaller negative number than -1, so -0.99999 divided by a tiny negative fraction, so divided by, say, -0.00001. So you will a negative number very close to 1 divided by a tiny negative fraction will be a huge positive number. And at 3 pi over 2, this is also negative pi over 2. If you go counterclockwise, it's 3 pi over 2. If you go clockwise, this is negative pi over 2. At 3 pi over 2 or negative pi over 2, here it's labeled as 3 pi over 2. Cosine will be 0, but sine will be -1. 0 over -1 is 0. And then very close to 2 pi, the cosine will be positive, but the sine will be negative and very small. Cosine will be positive and close to 1. The sine will be negative and close to 0. So you get a positive number close to 1 divided by a very small negative fraction. You will get a very big negative number. So you can see, but right at 2 pi, just like at 0, this cotangent is undefined because sine of x is 0 and cosine of x is 1. 1 over 0 is not defined. So you'll pretty much, this graph will repeat like so. But what's the deal with the arc cotangent function? Showed you what the cotangent function looks like. What about the arc cotangent function? So here I drew the cotangent function, but below here I've drawn the arc cotangent function. Now the question is, how did I get this from this? Well, the cotangent says you input an angle, and what is the cotangent of that angle? The arc cotangent function asks you input a number and you output the angle that you have to take the cotangent of to get that number. So this is saying, what's the cotangent of the number I'm inputting? This is asking, what's the cotangent of the number I'm inputting? And this is asking, what is the angle that I have to input to get a particular cotangent? And you can see these are reverse processes, and many times this is taught as when your inverse functions are reflections reflections about the origin. So for every point f of x equals, I'll just write it, where will I write it? So write it here. People think f of x equals cotangent of x and g of x equals arc cotangent of x, and we'll go over why this is capitalized again. This is actually the lowercase arc cotangent. These two are inverse functions. So you'll often see that this means that for every point, just abbreviate that PT, x, y on f of x, you'll have a point yx on g of x. And when I said reflected about the origin, I was wrong. I should have said reflected about the line y equals x. So I guess I'll give you an example here. So this is a line y equals x. Okay. This is y equals x. And I'm going to draw y equals 2x. Y equals 2x. And I'm also going to draw y equals 1/2 x. So this is a line with a, this is y equals x, the line in the middle. This line here is y equals 1/2 x. Okay, so here I have to make this a little bit clearer. This line in the middle is y equals x. This line here is y equals 2x. This line here is y equals, this line is y equals 1/2 x. Okay, that is this line here with a shallower slope. And you'll see that these are inverse processes here. And what that means is you can undo this y equals 2x by plugging in 2x for x in y equals 1/2 x. 1/2 times 2x is x. You just get x back again. These are inverse functions, and you'll see to get one from the other, you flip over the line y equals x. You have y equals x in between. Flip this over that line. So every point here, there's a point here. This point here, there's a point here. They both go through the origin. But you have a point here, then you have another corresponding point here. These points would be x, y, and these points would be y, x. Now, there's another way to think of that for cotangent of x and arc cotangent of x. So to get this graph of arc cotangent of x from cotangent of x, you'll have to flip over the line y equals x, and that's kind of hard to see in this case. It's not as easy to see as in the case of converting y equals 2x to y equals 1/2 x. But here's the way I like to think about this. Imagine what would happen if you rotated this whole thing counterclockwise 90 degrees. You're starting with squigglies that look kind of like this, right? If you rotated them, and this is the positive x-axis, and this is the positive y-axis. If you rotated this 90 degrees counterclockwise, well, this would end up here. It would turn into something like this, right? Whatever's here would end up here. This would end up here, and this would end up here. Like, imagine turning this 90 degrees counterclockwise. And this one that's on the right would end up on top. But what's in the plus? So you can see when you rotate this positive x-axis 90 degrees counterclockwise, it'll turn into the positive y-axis. So I'm just going to write positive x here because this is the rotated positive x. But the positive y, when rotated 90 degrees counterclockwise, will be placed where the negative x-axis was. So how do you get the positive y-axis to be where the positive x-axis was? Well, you're going to have to flip this whole thing, right? You're going to have to flip it. You're going to have to flip it over a line that's parallel to what was the y-axis. So now, what was the positive x-axis is now the positive y-axis. What was the positive y-axis is now the positive x-axis. What was the positive x-axis is now the positive y-axis. So this is after the 90-degree rotation and the flip. 90-degree counterclockwise rotation and the flip. So this is after 90-degree just going to abbreviate counterclockwise as CCW, 90-degree counterclockwise rotation and flip. And this is only after the 90-degree counterclockwise rotation. And this is the original. Okay, so now we have what used to be, because what was the y-axis is now positive y-axis is now the positive x-axis, and what was the positive x-axis is now the positive y-axis. We can be certain that whatever was a point xy is now a point yx and vice versa. And you can see this little schematic here is essentially this graph here. And this is the graph of arc cotangent of x, but without the capital sign. And I find this way of thinking about it is easier than thinking about flipping this over the line y equals x. In the case of the arc cotangent to arc cotangent conversion. But the issue here is this is not a function. This fails the vertical line test. If you remember from Algebra 1, you pass a vertical line through a function, through any relation. In order for it to be a function, it can't pass through more than 2 points on that relation. So is there any way we can restrict the domain of this original cotangent function so that its inverse arc cotangent can be a function? Well, yeah, if we restricted cotangent from 0 to pi. Alternatively, we could restrict it from pi to 2 pi. When we flip over the line y equals x, we'll only be getting one of these things rather than two. So you could restrict from pi. This is 3 pi over 2, and this is 2 pi right here. You could restrict from either 0 to pi or pi to 2 pi, and by convention, they restrict from 0 to pi. So the principal arc cotangent, capital, just looks like what I've boxed here. This is pi. This is capital arc cotangent of x, and they call this the principal arc cotangent. And so why is that important? Well, we're interested in the principal arc cotangent of the square root of 3, right? That's what, when we took the limit, that's what everything boiled down to, the principal arc cotangent of the square root of 3. Well, looking at this graph, we're going to have to see where do you think it equals square root of 3? Or I mean to say, what is the angle between, when looking at this graph, what is the angle between 0 and pi where the cotangent is root 3? So that's amounting to asking you here, what is the x value for which f of x equals cotangent of x equals the square root of 3? Or here it's asking you, what is the y value for g of x equals arc cotangent of x for which x equals the square root of 3? And this is 0, so you can see it's going to be somewhere between 0 and pi. And if you remember from your unit circle values, it is going to be, or between 0 and pi over 2. And if you remember from your unit circle values, it's actually turns out to be pi over 6. And this is because we'll just go up here. We'll say here, imagine this is the positive x-axis of the unit circle, and this is theta equals pi over 6 or 30 degrees. Well, cosine of pi over 6 is the square root of 3 over 2. And sine of pi over 6 is 1/2. Okay, so cotangent of pi over 6 equals this cosine of pi over 6, root 3 over 2, divided by the sine of pi over 6, or 1/2. And this is just root 3, the square root of 3. So the arc cotangent of the square root of 3, principal arc cotangent, is pi over 6. And I say principal because we are restricting ourselves to the region between y equals 0 and y equals pi on arctangent, or x equals 0 and x equals pi on the cotangent function. So y equals 0 and y equals pi on the arc cotangent, and x equals 0 and x equals pi on the cotangent. Both of those correspond to the area over the region over which the principal arc cotangent is defined. So this principal arc cotangent of square root of 3 is pi over 6, and that is your limit.